Alright, so let's continue reading this paper. And I'll start from here. So, as a simple application of this result, consider a spin 1/2 particle processing in a homogeneous magnetic field. In this case, the Hamiltonian is c squared. No, not that. Hilbert space is c squared. The projective space, P1 of C, is a sphere, and the Fubini study metric defined above is the usual metric on this sphere corresponding to unit radius. Blah, blah, blah. At any instant of time, coordinate axes can be chosen so that the Hamiltonian H minus mu sigma z and the state is psi cosine 1/2 theta sine of 1/2 theta. Okay, then from 2, which is the formula for the uncertainty in energy, is just mu sine theta, and from 1, Schrodinger equation, we get this relationship, which is the infinitesimal angle by which the state is rotated about the instantaneous direction of the magnetic field in the infinitesimal time dt. Hence, 2 times delta E times dt over h is d theta, is sine theta d theta, which verifies 8. Equation 8 gives a new geometric meaning to the uncertainty in energy delta E. For an arbitrary quantum system, ds over dt is equal to 2 delta E over h bar. This is the magnitude of the velocity of the system in the projective Hilbert space. So it's the velocity of the system. So if the uncertainty of the energy is 0, the system does not evolve. Steady state. The uncertainty in the system is large, and it does evolve. Velocity. So the kinetic energy is 1/2 mv squared, right? Two squared is 4, so that is 2 m delta E squared over h bar squared. That's the kinetic energy. Alright. It follows that the evolution of the system in P completely determines delta E. No other information from H is needed to determine delta E. On the other hand, the distance S given by 3, yes, that integral thing, is independent of even the rate of evolution and depends only on the unparameterized curve in P that is determined by the evolution. Also, the time energy uncertainty principle acquires a new geometric meaning as follows. To distinguish between two states in the history of the quantum system, it is necessary for these states to be orthogonal because they must be eigenstates of some Hermitian observable with different eigenvalues. Since the shortest possible distance between orthogonal states, which is along a geodesic, is pi, the actual distance s has to be greater than or equal to pi, where s is given by 3. For the actual evolution between the two states, this may be written as so what's s? So s is this integral so ds oops, that's h bar. Well, h bar is h over 2 pi, so that's where we get h over 4. Okay, time average uncertainty and energy. Time average uncertainty, so the average delta E. Mm-hmm. Okay. The inequality 9 is independent of our normalization convention for Fubini study metric. It is more stringent than the usual time energy uncertainty relation, which has h bar over 2, or that's h over approximately 12. Equality in 9 holds if and only if the system moves along a geodesic in P. In this case, the evolution may be said to have minimum uncertainty analogous to how a Gaussian wave packet is said to have minimum positional momentum uncertainty in a given time. More generally, we can define the efficiency of an evolution, epsilon, is S naught over S, where S naught is the distance along the shortest geodesic joining the initial and final points of evolution that are distinct points on P. Then epsilon less than or equal to 1, which contains 9 as a special case, but is valid more generally even when the system does not pass through orthogonal states. As an application, consider a double slit interference experiment in which we observe through which of the slits 1 and 2 the particle goes by letting it interact with a second system, which we take to be a spin 1/2 particle initially in the state sigma z equal 1, or spin up. The particle interacts with the second system if and only if it goes through slit 2. The Hamiltonian of the interaction is, so I have 2 slits. I have some particle. And then so slit 1 and slit 2, and then letting it interact with the second system, which is and then if it goes through, now I have a spin up particle here right after slit 2. Okay. The Hamiltonian of the interaction is g of t, okay, with sigma x f of n, where f of 1 equals 0. So if it goes through the slit 1, then the interaction is 0. If it goes through slit 2, then there is this interaction between g of t, which I'm guessing is some wow, sorry, there's just a shit ton of birds outside. I gotta check this out. 1 sec. Okay, that was pretty weird. Like an entire flock of birds. Crazy. There's so many birds out there right now. I have no idea why. When it's the middle of winter. Whatever. Okay, so g of t, I'm guessing, is some sort of... Okay, so this Hamiltonian is the interaction between sigma x. This is the interaction between a dipole interaction. Okay, blah, blah, blah. The corresponding wave functions of the particle will be denoted by psi1 and psi2, respectively. Then the wave function of the combined system after the interaction is this. Okay. So after we have the interaction, so psi1 is the wave function, I'm guessing, for slit 1, and psi2 is the wave function for slit 2. So initially, so we have So psi 1 spin up plus psi 2 let me get some sort of superposition. I'm guessing because this is so what's my initial state? Would be psi 1 and spin up. I think something like that, and some normalization. And then when I apply my Hamiltonian operator, I think so. This one, what happens? I don't really know how to get this, to be honest. Well, I think this part kind of makes sense to me, right? Because so I'm gonna get a 1 out front. This f of 2 will be 1. And then when this sigma x operates on sigma z equal to 1, I get this superposition probably. Okay, so I mean, I'll just concede defeat. Okay, from the left-hand side of 10, the distance along a geodesic joining the initial and final spin states in the projective Hilbert space of the spin when it interacts with the particle on using 6 is theta. Okay. From the right-hand side of 10, this difference is the phase difference between the particle state through slit 2 for the two possible spin eigenstates of H, which has a new geometric meaning given by 11. When theta is equal to pi, there is no interference between the two beams. Therefore, regardless of how weak the interaction between the two systems is, so long as the spin state undergoes a transition to an orthogonal state, the interference pattern is destroyed because of the minimum distance pi between the two orthogonal states in the spin projective Hilbert space. Since the inequality 9 expresses the existence of this minimum distance, the loss of coherence in this experiment is regarded as due to this time energy uncertainty principle. Okay, I did not understand that example. let's see if I can get this example. As a further application, we show how a quantum mechanical clock directly measures the Fubini study distance, and that time is derived from this distance. A simple model of a clock is represented by the normalized state vector. Okay, so j is a large positive integer. Okay. Why is this a clock? A simple model of a clock. This state vector passes through the sequence of orthogonal state vectors. So we say that eta t is equal to 2 pi m. Which may be regarded as the pointer positions of the clock. A possible Hamiltonian for the evolution 12 satisfies Hn equals n eta, n is this. Then from 2, delta E is this, which of course is independent of time. Therefore, from 3, this distance is this times time. Hence, the Fubini study distance between two successive states, 13, corresponding to the time interval delta t, is delta s, which tends to the universal value 2 pi over 3 as j goes to infinity. This limiting distance is non-zero, even though delta t goes to 0 as j goes to infinity. Also, it is greater than the shortest distance, pi. So t is really this it's a parameter, but it measures the clock. Since time is measured by the clock, really measures s. So the Schrodinger equation is, how does the state change with respect to this distance s, I think. So we don't need to think of time as a clock. The time as a clock is an analogy, or is an abstract way of thinking about, okay, whether we think of time as a clock or as time as a parameter which moves a distance s in this Hilbert space, they're the same. So a pointer moving on a clock face is analogous, or I guess you can think of it as either that, or you can think of it as moving some distance s in a Hilbert space. And the Schrodinger equation tells you how the state changes over this distance. Also, the greater delta E, the larger the change in S for a given change in T, and hence the more accurate the reading of time by the clock. So if delta E is greater, so S, so if so delta E goes up, then delta T is becoming more accurate. So if S is this tiny blip, delta T is very large. So it means that S is proportional to 1 over delta T. Remember there was the time was also proportional to 1 over temperature. Wait, delta T is the time interval. So if the time interval becomes very large, distance becomes small. Also, let phi be the variable conjugate to n. The inner product in the phi space is defined by this integral over the angle where g, then in phi space, the representation of n and phi of t are respectively alright, where x is hence for large j, okay, sharply peaked around. Indeed, that tends to direct delta function. The center of psi moves around phi space with constant angular speed, with its shape fixed. Therefore, the clock is well behaved at all times. From 15, omega is proportional to ds over dt, hence the measurement of s by the clock is in effect also a measurement of the angular distance traveled in phi space, corresponding to the displacement of its pointer position. Very, very interesting. All right, so that's the conclusion of that. Just a short one, I guess. So I'm gonna sit with this for a while, think about it, and probably do another video on some ideas.